terms that I'd like to introduce to you. Okay, over here, I'm going to call it stress 1. Okay, over here, I'm going to call stress 2. Okay, there's no reason why stress 1 is on the left-hand side, stress 2 is on the right-hand side. There's no reason at all. You could go the other way around. Stress 2 can be on the left-hand side, stress 1 will be on the right-hand side. It's fine. Okay, so stress 1 and stress 2 are known as principal stress. Okay, principal stresses. Okay, where the shear stress is equal to what? 0. Okay, so for principal stresses, the shear stresses are equal to what? Are equal to 0. Are we clear? Okay, they are equal to 0 in our principal stress. Okay, so that is normal stress. So like what you can see now, right? Like what you can observe now is that normal stresses, I should have written this earlier, my bad, is normal stresses are stresses acting perpendicular to the surface. Okay, so that is what we mean by normal stresses. Okay, so it's very straightforward, isn't it, for normal stress? Anyone, any questions regarding normal stress? Anyone? Are we good? Okay. The next one we're going to focus is on shear stress. Okay, and shear stress is not difficult. It's just yes.
So what you have said there, like principal as stress 1 and stress 2 are known as principal stress, and tau, where tau is equal to 0. What does that mean?
Shear stress is equal to 0. Right?
Okay.
If you look at stress 1 and stress 2, shear stress is equal to 0. So for principal stress, shear stress has to be equal to what? 0. Okay? Are you okay?
Yes, sir. Yes, sir. Got it.
Okay, got it. Okay, right. So the next one we are going to look at. Okay, so that's down. Do I have enough space? Yeah, we're going to look at shearing stress. I do have enough space. Okay, so we are going to look at shearing stress. So shearing stress sounds familiar, yes or no? Right? We calculate shearing stress so many times, and we also calculate normal stress also many times. So normal stress, if you look at normal stress, okay, normal stress can be equal to P over A plus by My over I Y Y Z plus by Mz over I Z Z Y. Yes or no? You guys say, oh no, not again, right? So it can normal stress, right? That's our normal stress. So shearing stress over here, it can be equal to what? Shearing stress can be equal to VQ over what? IT, right? So now you can see the values that you have calculated, okay, how to bring both of them together. Unfortunately, because of time, I wish I have 2 more weeks with you guys, but I don't. I will teach you how to integrate, but not for this class, okay, because of shortage of time. So if we look at the shearing stress now, right? If we look at shearing stress, so shearing stress, right? Shearing stress are stresses acting parallel, right? Parallel to the surface. Okay, they're acting parallel to the surface. So there's 2 configurations for shearing stress. Okay, so we have positive shear. Okay, so let's look at positive shear. Okay, so I'm going to draw an element. All right, and then we have our respective configuration, X and Y. So this is how our shearing stress look like. Okay, and I will put on the center another axis. Okay, so this is the local axis. Okay, where the center is 0. Okay, so this is X and this is Y. Okay, center is equal to 0. So what you see down here, we will call this arrow over here, right? The one, this is shear stress. Okay, the plane is intersecting the x-axis. The direction of the stress is in y direction. Okay, I will do the other one. Okay, over here you'll see you have a shear stress. Okay, the plane, the intersecting plane. What do I mean by the intersecting plane? This is the intersecting plane. The intersecting plane is y. Okay, and the direction of the stress is in what? Is in x direction. So this is what it means. Okay, so the first term over here is the intersecting plane. Okay, intersecting plane. And then the next one is the stress direction. Right? So it is always the intersecting plane first and then the what? Stress direction. Okay. So this is known as positive shear. Okay. So some of you say, you will ask me, Eugene, why positive shear? Okay. So if you look at this area over here, right? The area that is intersecting the x-axis is on the right-hand side of the 0, right? Is the right hand. So the area over here is equal to positive area, right? Right? The area in the x, right? So x is positive, and the stress is in the y direction, and is going up is also what? Positive. Okay. So if you look at the area, the intersecting plane, right? So I write here area of y is also positive. This arrow over here is going towards the right, is also positive. Okay, so that is why we call positive shear. If we look at the other end, if we look at this end, right, you will realize that the area is negative. The direction in the x direction, so the direction in the x is also what? Negative. So negative times negative becomes what? Positive. Likewise, the area is negative, right? The stress acting direction in the y is also negative. So negative by negative is positive, right? So positive times positive is positive. Negative times negative is also what? Positive. So if we were to draw the deformation pattern, okay, we draw the deformation pattern will look like this. So how do I know is that deformation pattern? Oh crap, this is hard to show now. Okay, if you put your fingers at both end of the arrows, okay, so if you put your finger, down here, two fingers down here, and you squeeze, right? That is your deformation direction. Okay, yeah, I this is where one thing that you need real life, you need bigger screen. Light board will help, I know. Right, so you guys, I'm going to stop sharing my screen now, and I don't want you to look at me. Okay, so now I stop sharing, am I right? Right, so if you
Yes.
okay, so you can see this, right? So you can see the arrow of the shear, yes or no? So if I take two of my fingers and I squeeze these two arrows, right? I will have a deformation in that direction. Am I right? Yes or no? Right? So I squeeze, right? my deformation is in that direction. So at the bottom also, right, you can see the arrow down here. And if I squeeze my finger, right, the two forces acting, when I just squeeze it, you can see the deformation is in the pattern. So that's why the deformation is that way. Okay, so let me go back to my screen sharing mode again. Okay, so now, how does this look like in Mohs circle? Okay, so again, we label this X, we label this surface Y. Okay, so we label that surface X, and we label that. So we know for this case, right, for this case, we have stress X is equal to stress Y, both are equal to 0. Shear XY is equal to shear YX, and now is equal to positive. Okay, okay, now is equal to what? Positive. My advice to you now is, in shear, don't take the positive and negative too seriously. I repeat again, in shear, don't take the positive and negative too seriously. And I will elaborate why. Okay. So now we're going to construct Mohs circle. Okay, we're going to construct Mohs circle. So this is our normal stress. This is our shear stress. Element rotate clockwise, element rotate anti-clockwise. And we know that the stress X and the stress Y line, right, is on the center. We know it's at the center. Okay, so this is the stress X and the stress Y line. Okay, it's exactly at the center. Okay, so now we have shear stress. The shear stress is positive. Remember, I told you, don't take the magnitude too seriously. Okay, so you draw, so no doubt I say it's positive. You have to draw the shear stress at the positive, and you have to construct the shear stress in negative. You have to draw two lines on the shear. Right. So now I'm going to go really slow. We're going to look at point X now on Mohs circle. Where is it? Okay, so where is it? So what I want you to do is I want you to lock the center, okay, or I want you to pin the center, okay. And if you look at this force over here, or this stress over here, it will generate the element rotate by what? Anti-clockwise direction. So for this case, over here, back to your Mohs circle, this is point X. Why this is point X? Because over here, we said that the element will rotate in a what? Anti-clockwise direction. So this arrow over here represents the element rotation. Okay, so that is our point. So now let's focus at our point Y now. Okay, so let's focus on our point Y. So if we now look at point Y, okay, I'm going to go slow. Look at point Y, right? If we use the same pivot point and you look at this stress over here, right? The one that I'm circling now. Okay, if you look at that stress direction, the element now will rotate what direction? The element now will rotate in a clockwise direction. So if you look over here, based on the element, right, rotation in terms of shear, clockwise is that. So this is your point Y. So from here, you can construct your Mohs circle. Okay, so this is your Mohs circle. So this is your stress 1, your principal stress, and this is your stress 2, your other principal stress, right? Right. So this is what we call positive shear now. So now you know what is positive shear. Now let's look at negative shear. Okay, so negative shear, I'm going to draw in the next page. So same, so I'm going to write this as negative shear. Before I go on, there is no such thing as positive shear is better than negative shear or negative shear is worse than positive shear. Both are the same bad or both are the